Welcome to workshop 14 on data structures and algorithms. In this section, we will talk about Huffman coding and its applications. The objective will cover understanding the basic techniques of data compression. We'll also talk about the data compression using hierarchical data structures. And lastly, we will look at implementing Huffman's algorithm for data compression. The main aim of data compression is to reduce the size. So in terms of reducing the size, we are referring to how we can minimize the number of bits. Different data types can be compressed. We can compress text, sound, image, and video. But for this lecture, we shall be focusing on how we can compress text. When data is compressed, the storage size is reduced, and it also becomes easier to be transmitted, which means the time it takes to be sent from one location to another will be reduced, and the time to retrieve it will also be reduced. So traditionally, this flowchart represents the steps for data to be compressed and decompressed. So the original data need to be encoded and then compressed. Then it needs to be decoded when it goes to the destination and decompressed. So for data compression, there are two basic types of data compression. One is the lossless data compression, and another one is the lossy data compression. The major difference between these two is that for the lossless data compression, when the data that has been compressed is decompressed, the original data is almost the same as the data that has been decompressed. But in the lossy data, the original data may lose some information. So sometimes you may not lose the accuracy of when it has been decompressed, because what might have been decompressed or removed during the process might be like noise in the data. So that will not reduce the accuracy or the quality of the information when it has been decompressed. So the typical data decompression we can group them into their areas, like the text decompression. So when we perform the text decompression, we can create a cookbook for it, which we can see during the Huffman's coding. We can also use a different method like creating a code word to represent the data that we have been decompressed. And we can as well use the vector number vectors to represent the data that we are decompressed. This is just an example of what we mean by code, number code. We can use this, like for instance, A can be represented with 00, B can be represented with 01, and likewise C and D. So for the vector, for instance, we can represent apple with the vector value of 30, 123, and 345. So these things are what we can use to represent the code. And we have a question here. We said, what happened if we use lossy data compression for test? This kind of test compression is used mainly for language processing. And then let's look at another type, which is the voice compression. So the voice compression could be applied when we need to perform transformation from time domain signal to frequency domain signal. We can also use it when we want to perform some approximation on data. So this the time domain signal can be transformed to frequency domain signal, and that will remove the unwanted frequencies. And when that is achieved, we can take it back to the time domain signal and use it the way we want to use it. So for references or for areas where you can get more information regarding this kind of data compression, you can have a look at this reference, these textbooks by Alan V. Oppenheim. So it can be used for image processing, and another area we'll be looking at the video. So for this image procession, we can use it to reduce both the space, color space, the RGB conversion to vectorization. We can also use it to reduce the size of the pixel from, for instance, we can reduce 20 bit to 8 bit, depending on what we want to achieve. So this is just like an example of the kind of reduction that can take place. So this is an original image being reduced to half, and the original the half is being reduced to another half. So if you have a look at these three images, you might realize that there might be reduction in quality, but it doesn't lose the information that it needs to provide. There's also a source for you to have more information regarding this. Apart from that, you can also take a course on this from the School of Computing. So now let's look at how we can decompress some data. One approach is by using fixed length coding. So in the fixed length coding, let's assume we have been given a string of data that has this character. For that string of data, we have A, U, Z, and X and Z. So in this case, the character that we are referring to, say that the character has 1,000 characters of string. So if we want to send this data without the compression, so the storage is going to be 8,000 bits. Why it is 8,000 bits is because we have 1,000 characters, and each character has 8 bits. So the value of the storage is going to be 8,000 bits. But if we have to decompress these data, these characters, we can have the character represented using 00 for A and 01 for Z, then 10 for U and 11 for Z. So in this case, we have reduced the number of bits for each character to 2. So what we now have, what we're going to have is that we're going to have bit, which is going to be 2 times 1,000. So if we multiply by 1,000, we're going to have 2,000 bits. Then the storage for the table is giving us 48 bits. So the total number of bits we're going to have will be 2,048 bits. So this is because we have 1,000 character comprising of A, U, Z, and X and Z. So and each of them has 2 bits. So if we multiply each of them, we're going to get 2,000 bits, and the size of the table for our conversion is going to give us 48 bits. Now, if we compare these, we can realize that the difference in terms of ratio for the compressed and the uncompressed data will be approximately 4:1. So there's a question which says the compression ratio is fixed and independent of the frequency of each character. In the next one, we're going to have a look at how we can encode and decode this string. So we have been given a string here, and we want to see how we can code and decode it. Now let's start. Now we have that each of these code has been converted to 2 bits. Then how do we encode it? We're going to encode it by using these 2 bits of the code to represent this. So for instance, we have AA. So we're going to have 00 and another 00 being represented here. Then the next one we have is X, and that X is 01. So the one after X is 01. The one after X is U, and we have our U to be 10. Then we have A again, then we have X and Z. So for us to encode this, we use 14 bits. Now, if we want to decode it, it's just picking off those pair of bits from left to right. And when we pick it up, this is AA, then we have AA, X, U, A, X, Z. So the lossless compression, that is to say, we did not lose anything after our compression and decompression. But this is a case of a lossless compression. Apart from the fixed length coding, we can also perform variable length coding. So in the variable length coding, we use code word to represent the characters depending on the length of the frequency occurrence. So those characters with longer frequency or more frequency occurrence will be represented with shorter code words. Those characters with shorter frequency occurrence will be represented with longer code words. So we can have a look to see an example of how this can be achieved. As the question says, does the variable length coding necessarily reduce the size or increase the compression ratio? From what you're going to have in subsequent slides, you will be able to answer this question. We have been given a string of these characters, and using the variable, we have to find out what is the frequency of each of these characters. So if you have a look here, we can see that A occurred 3 times. So we have the frequency represented with 3. And Z occurred twice, so the frequency is represented with 2. Then U occurred once, and sorry, X occurred twice, U occurred once, and Z occurred once. So we represent these are the frequencies. Then we have to find out the one with higher frequency. The higher frequency starts with A. So we're going to represent it with lower code words. So that is why we have A represented with only 0. The one that is following it is X. So we have X represented with 10, that are 2 digits. Then the rest of them have only 1. They occurred once, so we represent them with 3 digits. So for us to encode these, we can encode them using this to encode this string. Then we have to encode using A occurred twice, which is 00. Then X occurred once, which is 10. Then we have U occurring once, which is 10110. Then we have A again, which is 0, and we follow the pattern until we get to Z. So now, if we look at the length of the bit that we have, we can see that the bit has been reduced to 13. But in the fixed variable length, the bit for this particular string was 14. So there is a reduction in the bit. So if we perform another operation, just be careful. You can see this is the frequency that we have for the characters. So for the fixed, we are now comparing the fixed and the variable length. For the fixed length, we have 2000 bits. Then for the variable length, we have 1006 bits. So this is how we got that of the variable length. Then if we perform similar operation again here, for the fixed length, we have 2000 bits, but for the variable length, we are having 2180 bits. Can you see the difference? So this is trying to say that if care is not taken, then the variable length will not give shorter bits at all points. So in that case, what do we need to do? We need to be careful when we are choosing or designing how the size or the frequency need to be read. Sorry, when we are designing our code book. Let's now decode our string from these values that have been given. So for us to decode the string, we need the character code book. And this is a character code book given to us, where A is represented with 0, X is represented with 10, U and Z are also represented with their own code. So what do? We have to start. If you look at this code, you can see that 0 is here, and we have 00, and we have 001. So these are the three possible values that we can start with. So that's the reason now we say we do not know how many bits to pick off. So are we going to pick up 0? Or are we going to pick up 2 bits? Or are we going to pick up 3 bits here? Now, for us, we have to consider these are the possible. We can pick up 0, we can pick up 00, or we can pick up 001. So, but when we look at our code book, we can realize that there is no value with 00, and there is no value with 001. So possibly we can have A. So we have A, and we're now left with the rest of this. So if we repeat the same thing, we can also see that there's no value that has A. Sorry, there's a value that has A, but there's no value that has 01, and there's no value that has 010. Let me go through it again. I mean, we have already picked up A, so we are left with value with this code starting from this second one, the one on yellow. Now, for us to pick, we have to check the 3 digits, which is 010, which has no representative here. And we can also say 01, which has no representative here as well. Then when we check 0 only, we can see that A has this as 0. So in that case, we can conclude that we can take the next character to pick must be A. So we can continue this using this pattern until you get to the end. The question is, will you retain or restore the string that was originally given? So try and see if you can restore the string. If you can do that, that's very fine. If you have a different string, then you have to discuss that with Darlene. Okay, now let's look at the Huffman's coding. So the Huffman coding is just a statistical way of compressing data, and it makes use of the variable length bit string. So it works by recognizing the most frequently occurring characters and converting them using short code words. Then the least frequency occurring characters are converted using longer code words. So the steps for generating Huffman's code is, first we have to create a Huffman tree. And when we've created a Huffman tree, we have to identify the leaves and the edges of the tree. And after identifying the leaves and the edges of the tree, we can perform the path tracing from the root to the leaf in order to get the Huffman's code. So more explanation is being given on how to achieve that. So now let's now look at the how we can create Huffman's tree itself. So initially we have a forest of leaf nodes containing the character and their frequencies. So in this case, we have a kind of a list of or random numbers of leaf nodes with their characters and frequencies. So now we create the tree by first sorting those leaf nodes based on their frequencies. Then we identify the two nodes with lowest frequencies and combine them together. When we have combined them together, we check the next two nodes with lower frequencies and combine them together. That's how we keep on repeating until we get to the last node. There is an example that will explain better how we can use this operation or perform this operation. Another thing is that we can also apply the heap data structure using the priority queue that we discussed in the previous workshop. So this is just an algorithm to explain more about the steps that we need to take. So the algorithm says that we need to insert the nodes into a mini heap, and we have to remove some of the two nodes with the lowest frequency from the heap. Then we create a new internal node that is kind of sorting the new nodes in order to get all of them in the same to make them aligned. And lastly, the last node will be used as the heap root node. The next slide, it will give you a clearer view of all these algorithms. So let's now have a look at the example, which will explain better all that we have said. So this is the forest that that was referred in the other slide. So if you look at this, we have the data with their corresponding frequencies, or the characters with their corresponding frequencies. So from these characters and their corresponding frequencies, we have to create the Huffman tree. And we have to do that by starting from left to create a mini heap. So if you look at these things, you see that the highest is 66, followed by 64. So we arrange them in this ascending or descending order. And once we are done with that, we can now bring all of them to form the leaf of a tree. We bring them the way that they have been arranged to form a leaf tree. And the next step we need to do is to find which of these two of these nodes have the lowest values. They are 12 and 9. So we have to combine two of them. So when we combine 12 and 9, we get 21. And once that is done, the 21 we replace 12 and 9. So from this list, which of them have which of the two nodes have lowest values? They are 23 and the 21. So this is 23 and this is 21. So we're going to link both of them together and we have 44. So 44 is representing the whole of days here. Then in this list, which of them of the two have lowest values? So they are 32 and 29. So 32 and 29 need to be combined to get 61. So 61 will come to this place. So we continue that way until we get to the last number. So that last element is the one that has the mini heap, and that will represent the root node. So the next thing we might have to do from this point is to determine the Huffman code from this character or from this Huffman tree. So how do we determine the Huffman code for this? So the thing we have to do is that we have to label them. We have to label all the edges using either 0 or 1. Now we have labeled them with 0 and 1. And how did we label them? We labeled them by saying that all the edges at the left will be labeled with 0, and all the edges at the right will be labeled with 1. So if you look at this place, this edge is at the right, so we label it to 1, and this edge is at the left, we label it with 0. So for us to identify each of these values or each of these character, their corresponding Huffman code, we have to follow from top to the leaf node. So if we want to start with F, for instance, F is 0, 0, so represent it with 0, 0. Then B is 0, 1, so that is represented with 0, 1. Then C is 1, 0, 0. So we continue with the same pattern until we get to E, which is 1, 1, 1, 1. So this is how we can represent or determine the Huffman code for the character directly from the Huffman tree. And this is an activity which you are advised to try your hands on. So during this activity, you've already been given the string, and you need to create the Huffman tree using the string. Remember, you need to consider the frequency. And after creating the Huffman tree, you need to decode the tree to get the code, the Huffman code. And lastly, there is a question here which says, is there more than one answer to this activity? If you say yes, you can say yes or no, but you need to justify your answer. So this has just given you a clue of the steps you need to take. And there's an activity here which is showing you how you can generate the code, the Huffman code from the tree. So the same pattern that we used in the previous one. So if you want to generate the Huffman code for A, so we have to go to A is 1, 1. And B is located somewhere here. So B is just 0. So which is 0. Then let's look at D. So D is here. So we have to follow this path, which is 1, 0, 0, 1. That is why we have this as the result.